Greetings, folks. So in this video, let's talk about one of these linear programming problems. Okay, so again, linear programming, it's a fancy word, but all it means is that you're trying to optimize something. Again, optimize just means I want to make it the best that it can be. Now, sometimes that means making a certain number as big as you can make it, and sometimes it's making it as small as you can make it. It really depends on the situation. Okay, so and it's a linear program because the thing that you are maximizing is a linear function. And we'll talk about that in a second when we get to our specific example here. Excuse me. Okay, so in this example, you're going to buy some new cabinets to store your clothes or your toys or who knows what. Okay, so you're shopping around and you kind of really like these two cabinets for whatever reason. Maybe you like the design of them or whatever. Okay, but you have two. You boiled it down to these two options, and you're gonna have some combination of twos. You know, both of them kind of fit the color scheme or design of your room, and now you want to you figure out what is the best combination of them. Okay, so let's break it down. So we know cabinet X, each one of them costs $10. Each one takes up some space in your room, right? 6 square feet. So again, that's like a footprint, and it also holds 8 cubic feet of stuff. Okay. Cabinet Y, it's a little more expensive because it's bigger, right? It costs twice as much. It takes up a little bit more in your room, but it holds more as well. Okay, so let's suppose that in your room, you've marked off 72 square feet. So that's going to be related to this. So maybe I should actually color these in a way that matches. So let's do these in yellow and these in blue. Right? You've marked off 72 square feet for your new cabinet. So that's the footprint that you're gonna put these cabinets in. Remember, you cannot fill your entire room with cabinets because you have no place to sleep and just walk around and stuff. So your room, who knows how big it is, but you've marked off 72 square feet of it for these cabinets. You also have a budget, of course. So you're gonna spend up to $140. It's okay to spend less. You can spend exactly $140, but you cannot spend over, right? Maybe you're like a college kid on a budget. Okay, so the question is, what is the best combination for us? And again, for us, the quote-unquote best combination is the number of cabinets or the combination of cabinets that maximizes the amount of stuff we can store, right? So we're going to make it as big as possible. Okay, so again, the goal of the problem is to, well, I underline it in green, right? Our goal is to find the combination of cabinets. Again, that's going to be some cabinet X's and some cabinet Y's that let me store the most stuff. Okay, and that stuff will be measured in cubic feet. So cubic feet. Okay, so that again, I wrote this problem out or the questions out in this order because again, this is kind of one of our first examples. Definitely want to write the questions in a way that one leads into the next. Excuse me. Okay, so remember, we have 3 variables here that we really care about. We're going to buy some amount of cabinet X's and some amount of cabinet Y's. Those 2 things together are going to affect how many things we can store. And you might be wondering, well, what about these other things? The cost and the amount of space they take up. Well, those aren't actually variables though, right? And again, you might think of that, well, the cost changes, right? How much money I'm spending will change depending on how many cabinets I have, and which is true. But again, that key word at the end is that the amount of money you're spending depends again on the number of cabinets you buy. The amount of space you're using up again depends on how many cabinets you have. So it all boils down to the number of cabinets you have, and the thing that you actually care about is the amount of space that we can store. So my 2 independent variables are the number of cabinet X's, and I think it makes sense to name that X, and then again Y will be the number of cabinet Y's. I'm just going to abbreviate it. The thing we're trying to optimize is the amount of stuff we can store I'm just going to say S for cubic feet of stuff. Okie dokie. We're going to want to create an equation for this to represent this. So remember, the amount of stuff that I have, or sorry, that I can store depends on X and Y. So I can actually write it this way if I want to be really fancy with it. S of xy, similar to our typical function notation, is just now, instead of that variable depending on just x, it also now depends on y. And so that's how you would write it. You don't have to. If you just wrote s, I would be okay with it, right? But let's see, each cabinet x has 8 feet, or can hold 8 feet, and each cabinet y can hold 12 cubic feet. Okay, so that's going to be our function that we're trying to make as big as possible, right? So our goal, again, coming back from this step up here, our goal is to make x, sorry, not x, but s as big as possible. But we obviously, so you might think, okay, well, I'll just buy thousands and thousands of cabinet x's and y's, but we can't actually do that because there are some constraints. So let's write that in blue. Sure, we'll do blue. Right, so what are our constraints? Right, so those, they're kind of hidden in the problem. I didn't just say straight up, there are your constraints, but your constraints are actually in this first sentence right here. Okay, so our constraints. So I'll give myself a little bit more space here before we get to our graph. So we marked off only so much square feet for our cabinets. So we cannot go over that feet, over that amount of square footage. So the way I could write that is for one constraint for the space they take up. Space taken up, I'll just disregard that. Like so. Okay, so similar to how we did the other one, right? For each cabinet X, it takes up 6 square feet. For each cabinet Y, they take up 8 feet, again for each Y. I need that number, and I'm going to add them all together to figure out how much total area I'm taking up. However much space they take up, it cannot be more than that. It cannot be more than 72. So it can be less than 72, and that's fine, but it could also be equal to 72. And so that's why we'll use that symbol, less than or equal to. Constraint number 2, we allow ourselves to spend up to 140. So again, the amount of money we can spend is going to be less than 140, which it would be allowable, but it could be equal as well, because equal is not more than. And so that's okay. I'm back. Sorry, I'm getting a little ahead of myself. So again, this is our budget constraint. The amount of money we spend, again, for each X, we spend $10. For each Y, we spend $20. We can actually simplify this, and it's going to help us when we graph it. If I divide the entire equation by 10, I will get just 1x plus 2y is less than or equal to 14. Okie doke. We can actually divide this one as well. We could divide the entire equation by 2, I believe. And we'll get 3x plus 4y is less than or equal to 36. Okay, so these are our constraints that we're going to play with. There is one more that we should actually consider, or actually 2. And I always like to call this one the maybe just common sense constraint. And this is pretty much always going to be the case. Well, I guess I shouldn't say always, but in most cases, right? We also cannot have x and y be negative. They could be 0, but they could not be negative because it wouldn't make sense to buy negative cabinets. Maybe you could think you're selling them back, but that would be also kind of weird, I think. So x and y need to be non-negative integers, and that's why on my graph here, I didn't even bother drawing any other quadrants. I just need to draw the top right, the first quadrant. Okay, so I'm going to graph these 4 inequalities, and I'll be right back. Alrighty, so I have graphed our constraints. So I actually color-coded them just so we can see a little bit more clearly what's going on. We have 3x plus 4y less than or equal to 36. That one is in red. And the budget one, x plus 2y is less than or equal to 14 in blue. And I didn't bother writing the common sense ones because we know that that's just going to be, x and y got to be greater than 0. So that's going to look like this, going up inward. So hopefully you can see that our feasible region is in here. Now I want to be really clear. We also are not going to buy only partial cabinets. This company is not, the company you're buying from is not going to have just, partial cabinets or broken things or anything like that. So the feasible region here should not actually be every single dot in this yellow area, but instead should just be the dots where the x and y values are integers or whole numbers. Okay, but just for ease of use, we'll just highlight the whole thing. Okay, so remember, everything inside here is a point or a combination of these cabinets that will fit our constraints or restrictions. Okay, but we want to see specifically, so there's more to the question, but I don't remember exactly what order the questions are asked. So again, our goal is to make this number as big as possible. I'm just going to remind ourselves that s, which is a function of x and y, is 8x plus 12y. Okay, so again, this is a 3-variable equation, so it'd be really awkward to draw. If we would need to draw in 3 dimensions, which I won't go into that in this video. But what we can do, remember, is say, okay, let's just pretend I want s to be a certain value, a certain number. So let's pretend s is equal to 50 cubic feet. So then that equation changes a little bit. So 50 is equal to 8x, plus 12y. This is a line now, right? All we have to do to graph it is find its x and y intercepts, like so. Alrighty? So I believe the x-intercepts on this one, the x-intercept, right? So set y equal to 0. X-intercept is going to be 50 over 8, which is what? If I could divide, let's see, top and bottom by 2, so that's going to be 25 over 4, so that's going to be 6.25 or 6 1/4. Okay, so that's going to be something like so, 6 1/4. It's going to something like so. Oh, sorry, x-intercept. 6 1/4. Something like this. Okay, now my y-intercept. So I'll set 50, x equal to 0, y-intercept, and I get 50 over 12, divide top and bottom by 4 again, by 2, I'll get 25 over 6, so that's going to be, 6 1/6, which is about 6.16 repeating, right? Okay, so that's going to be a little over 6, something like so. And so this is what our line should look like for that specific value of s. Slight mistake. My y-intercept should actually be 4.16. Excuse me. So hopefully you caught that before I did. So that would be somewhere around here, I believe. Okay. So this is what our line should look like. And something like this. Okay. So let me put that ruler off to the side. Now, remember, every point on this line shows me a combination that gets me 50 cubic feet. Again, every point. So this point right here, this point right here, this point right here, they'll all give us 50 cubic feet of stuff that we can store in these cabinets. Okay. I won't go too much into this video, but one thing we noticed in the class, or if you watched the previous video that I linked from, oh my gosh, I forgot his name, but where he talked about it and he had a really good explanation for it, is that if I was to say graph it where, let's say I want to see the combinations that get us 100 cubic feet, what would happen? So if I were to create that equation, I get 100 equals 8x plus 12y. What's neat about these two equations, is that they will actually have the exact same slope. And you can tell because, well, how would I get how would I find their slopes? Well, one way is I can find the x and y intercepts and then use delta y over delta x for those 2 points. But I can also just rewrite the equation. So for example, on this one, I would simply subtract x and then divide by 12 to get y by itself. And then your slope would be 8 over 12, negative 8 over 12. To get the slope of this line, or convert it to slope-intercept form, I would do the exact same thing. And so you'll move the 8 over by subtracting 8x, and then you'll divide by 12, and the slope on this one will be negative 8 over 12. Which means, the reason this is helpful is because this line, the slope of this line for any given amount of space that you can store will always be parallel to all the other ones. So if I have 50 cubic feet, it's going to look like this. If I have maybe 30 cubic feet, it'll look just maybe somewhere down here. If I have 100, it's going to be, a little bit higher because I can store more stuff and so on. And again, we want to make S as big as possible. So again, as S increases, we're going to go up this way, right? Which again should make sense because more cabinets means you can store more stuff. So I want to basically push this as far as possible while staying within the feasible region. Okay, so I'm going to go here. Can I go? So I hit this vertex up here on the top right here at 0, 7. Can I go more? And yes, it does. It looks like I have more space to go. So I'm going to keep going. I go here till I get to this vertex right up top here at 12, 0. Can I go further? The answer is yes, because I still have a little bit of yellow left to cover. And you can see I'm going to barely still be in the feasible region right here at this corner, like so. Right there, which is at, it looks like it's at, I can't see, 8, 3. And so that tells us that 8 cabinet X's, and 3 cabinet Y's will let us, or let me, store the most stuff. And that is the end of our problem. Now, if you want to know how much stuff how much stuff can I actually store, then you can just take 8 and 3 and plug it into our storage space function. Okay, now do I have to actually draw that line every single time? Not always. It is handy sometimes, and here's in the case where it is not handy, right? So you might have noticed that the best possible place that you could have gone is, again, somewhere that's up and to the right? Because again, more cabinets means more stuff. Now, it becomes slightly less obvious though once you actually get to the boundary. Because how do I know that this point right here, 0, 10, isn't better than 8, 3 or 12, 0? And your answer is at the very, very beginning, you don't, right? But what you could do is you could just simply check all 3 of them and see which one gets you the best answer. Again, best being whatever you're trying to figure out. In the case where maybe there are a lot of points, you might not want to check all of them because it takes a very long time. And that's an instance where probably sliding the line along, sliding the parallel lines as far as you can, and then just seeing where it ends, that's an example of where that would be better, probably. Save you a little bit more time, okay? So hopefully this example was helpful to you, and hopefully you feel prepared to try some more.